Cédran, Thierry Cédran. Okay. And we all gave 4 different, very different. Okay. So I think there will be 4 parts for the exam. For each teacher, that's it. But actually, I really don't know how important will be my part. I don't think it will be that important because you only have 4 hours with me, right? And you may have more time with the other teachers. So each teacher will prepare the exam, and then we will have all the 4 parts of the exam during the main exam. So this is how things will take place. But don't worry, I don't think that my part will be that difficult. I have done this class several times and I never had any problem with the students and bad results. So I think it will be, it will be okay. I hope it will be okay for you.
Are we continuing the lecture from the last time you were teaching?
Yes.
Okay.
Yes.
So we need the slides.
So what you have to remember from the last class is that we have cement, plus water. And if you have that with aggregates, you have concrete. And in this class, we will focus on cement and cement chemistry. We have a specific notation to explain cement chemistry with C meaning calcium oxide, S meaning silicate, A with aluminate, and F is ferrite iron oxide. Okay, so we use this specific notation to describe the different phases we have in the anhydrous cement. So we have 4 main phases, C3S and C2S, C3A, and C4A. So these phases, they are apart from what we call the clinker. And clinker makes most of what we call cement. When we talk about cement, we mostly talk about clinker. But actually, cement is different from clinker. Cement is clinker plus gypsum as setting regulator. And what we call secondary cementitious materials, SCM, secondary cementitious materials. And these secondary cementitious materials, they are constitute cements, but different type of cements that are defined by a norm, French European norm, 196.1, 1961, I guess. No. 197. This is a norm that defines the different type of cement. Cement made from clinker, gypsum, and maybe other secondary cementitious materials. And the clinker is made of 4 different mineral phases: C3S, C2S, C3A, and C4A. And these mineral phases, they are made of calcium oxide, silicate, aluminate, iron oxide. Okay? So this was the general context of cement. And now we are going into cement hydration. We have started a bit to talk about cement hydration during the last class, but we will resume from the beginning. Okay. So, cement hydration. The hydration of cement is the reaction between water and cement. The reactions are very complex, and that is why we will not go into details, especially regarding thermodynamical points. But you have to understand you have solid anhydrous phases in contact with cement. You have dissolution of the solid anhydrous phases. They will release ions in water. And these ions in water, they will react and precipitate to form hydrated phases. So we are going to anhydrous solid phases. Just water. Dissolution. Precipitation. And we got what we call hydrates. And it's solid. You understand my writing?
Sure.
Okay, so anhydrous solid phases plus water. You have dissolution, and dissolution means ions in water. And these ions, they react precipitation, and you get solid phases. So, very important, cement hydration is exothermic. And the fact that it is exothermic, that means it releases heat. We can follow the path of the reaction. The reaction liberates heat because of the reaction between aluminates and sulfates, meaning the reaction between C3A and S3 from gypsum. Sulfates react with C3A and gypsum, and we will go get to this reaction. So the consequence of hydration: one, we are going to the fluid step. Your cement is liquid with water. To go to the second step. This is the setting. But after the setting, we have the second step, that is hardening. That is the development of mechanical strength, because it's not because your cement paste is set that it is fully chemically developed. And sometimes after a few hours your cement paste is set, it's solid, but it's very fragile and it breaks very easily. Okay, so we'll go into the different steps of cement hydration. And by cement hydration, we mean hydration of clinker phases, and we begin with C3S and C2S. That means the silicate phases, the carbon silicate phases, because of course the presence of C, calcium oxide, is very important because this is the element that trigger the reaction because calcium oxide is reactive and silicate is not reactive by itself. So you don't have to remember these equations. This is just an example of what can be the equation with the stoichiometry adjusted. And just know that H is not hydrogen, it's water. And C3S reacts with water to form what we call CSH, calcium silicate hydrate. And CH, that is carbonate, or calcium dihydroxide, CaOH2.
So I'm sorry, what have you written? Portlandite?
Yes, Portlandite. This is the name of this mineral. Calcium dihydroxide, Portlandite, CH, whatever you want. Most of the time we call that Portlandite. And CSH, they are all CSH. They are very different stoichiometry, and we see later what it means, but calcium silicate hydrate, calcium silicate H, water, so hydrate. So you have the reaction of C3S and C2S with water to get CSH and CH. And you can write that any way you want. That means you can write, if I ask you during the exam, what is the hydration of the clinker? And if you write, oh, these are the equation of the hydration of clinker, and you write that, I'll be alright. If you write with what, if you write C2S react to water to give CSH, SCH, it also will be okay. So don't worry. But this is I think it's a very convenient way to remember the reaction. It's not a very well-defined chemical reaction. It's just a cementitious reaction. Okay, C2S or C3S plus water, CSH plus phosphate. But I think it's better to say that what CSH is and what protein that is. But it will be in the case of the question of the exam. Okay. So, what are CSH? Hydrated calcium silicate. This is the main compound of the hydrated cement paste. It forms 50 to 75% of Arden cement paste. And it gives the major contribution to mechanical properties of cement paste. Then we have Portlandite, CaOH2, CH. It makes roughly 25-27% of Arden cement paste. And once again, when I said Arden cement paste, we have to understand that it's only clinker, and then later we will see the case with when there is a secondary cementitious content. But here, Portlandite, it is 25-27% of Arden cement paste, and it plays a major part in durability. How? Because pH in concrete for a solution is around 13. So it's a very basic pH. And you know that water in the environment is mostly around 7, and even sometimes even more acidic, around 7, 6, or maybe 5. So it is very, very acid to concrete, very aggressive to concrete. So water destroyed concrete, water destroyed the cement paste. And what is the defense mechanism of the cement paste to water aggression? It's the dissolution of Portlandite. Because if Portlandite dissolved, we get calcium released, and also two hydroxide ion released. And these ions, they increase the pH. And so the concrete will reach again a pH around 30. So if you put concrete or a cement paste sample inside a tank of water, the Portlandite will continuously dissolve until it reaches again pH of 30. So if you put your cement sample into a very big tank of small cement sample into a very big tank of water, you can almost dissolve all the Portlandite because there is not enough Portlandite to change the pH of all the water in the tank. But if you have a smaller tank of water and a smaller piece of a bigger piece of cement, the dissolution of Portlandite can make the pH of the whole solution go higher and reach again 13 pH of 13 that is good to concrete. Okay, so this is a very important part of Portlandite, major part in durability. And the part of CSH that make the most contribution to mechanical properties of cement paste. Okay, I had the yes.
So if you add water to the concrete, it will dissolve Portlandite
Yes.
till the pH of the water is too high, and then the Portlandite won't dissolve. Or I'm
Yes.
not sure.
Once the pH is right in again, Portlandite will stop dissolving. And if you dissolve all the Portlandite and still the pH is too low, you will start to dissolve the other hydrates of the cement paste, and especially the CSH that will also start to dissolve. But before dissolving the main part, that is the CSH, the Portlandite will dissolve first in order to increase the pH. Okay, so the hydration kinetics of C3S and C2S. So C3S hydrates faster than C2S because C3S contains more calcium oxide than C2S. And calcium oxide is a reactive bond. So it will consume more water and for more hydrates, more CSH and more Portlandite. So maybe I should start with. So we will start by talking about CSH and the stoichiometry of CSH. So the CSH of cement, calcium silicate hydrate, they are formed in a very specific environment, as I said before. This is the cement paste. So it is very, we don't know the precise geometry of the CSH of the cement paste. We have examples of natural CSH like soberanoids and all those minerals are CSH with different different percentage of water, calcium oxide, and silicate oxide. We have tobaccoate and genate, I don't know if it has genate here. We have synthetic CSH, and CSH obtained in labs by various I don't remember the word in French. Anyway, various preparation of minerals in lab. So you mix calcium oxide, silicate, water, for example, and you get a CSH that you have a geometry close to CSH1 or CSH2. You can also get CSH in the lab by having pure C3S and hydrating C3S. But if you have pure C3S and hydrated C3S, as we've seen, you will get CSH but with photon. Okay, so what we know is that the CSH from cement paste is quite close in geometry to what we call the specific CSH, that is tobaccoate 11 angstrom. And 11 angstrom, it refers to the CSH is composed of sheets, and the distance between those mineral sheets is measured in angstrom. You know what an angstrom is? 10 minus 10. And it's very used in chemistry because this is 1 angstrom, but this is the size of an atom. So this is why we use angstrom. And so the A with the point, the Swedish A, angstrom, is the distance between the layer of the CSH. So here we have 11 angstrom, and here you have 10 angstrom, 9 angstrom. But we know by research that the CSH from cement, even though we don't have the specific stoichiometry of the CSH from cement, it's quite close to tobacco. But some other researchers say it's closer to shaded geometry. But you don't have to remember that. Just know that CSH exists in various forms. They exist as natural minerals. They exist in cement, but in cement we don't know the specific geometry of this CSH. Because
what does A stand for again? The distance between
between the layers of you have the calcium layers and the silicate, and the 10 angstrom is the distance between the sheets of calcium oxide and the sheets of silicon oxide. And it is 11 angstrom. And 1 angstrom is
Can you
No,
rewrite
it's
that?
not
You wrote
10
that too
angstrom.
fast.
What?
I said you erased it before I could finish writing what you just wrote. That, like, just wrote one.
Oh, I did my full drawing about. You have
Yeah.
calcium oxide sheets, and then you have silicium oxide sheet, and you have the distance between the two, and it is 11 angstrom.
It's typically 11.
There is a mineral called tobaccoate, 11 angstrom.
Okay.
The distance of 11 angstrom, and this is the closest we can get to the actual geometry of the CSH from the cement paste. So, and also the
You said it's 11
an accurate equation for the precipitation of CSH. So you see, this is the reaction between alkaline ions, calcium ions, and silicon ions. But you don't have to remember that. It's just for the culture. So these are some spanning electronic microscopy observations of CSH. So CSH, they are amorphous. So this is crystalline, this is amorphous. So this is not CSH, it is calcium carbonate. And these are CSH. You can see also here that it's not crystallized, it's roughly like alveolar sponge. Maybe. The structure of CSH depends on the calcium silicate ratio. And it's very important. So, calcium silicate ratio. For the CSH in cement, it's around, once again, we cannot determine this ratio precisely because cement is a specific environment with a specific condition, and CSH is not the only hydrate we have in the environment. But the calcium silicium ratio of CSH from cement test is of, I do that because we're talking 1.7. Okay. If you have a ratio, CS ratio over 1.5, it means your CSH are not pure. You will have CSH and carbonate. If you are lower than 1.5, you will only have pure CSH. I mean pure by, you won't form other compounds. You will only form CSH. They may not be pure because CSH are from calcium oxide, silicate, and water. So silicate and calcium oxide are rather stable in the environment. Calcium oxide is not stable in the environment because calcium oxide wants to react with carbon dioxide to form calcium. So that's why you see calcium here. These are CSH are made in the lab, and they were carbonated. The calcium oxide I've used was carbonated. That's why we can see calcium here. But if you carbonate CSH, you will form another geometry of calcium carbonate that is called platinate. But it's not much to remember. Just remember that CSH carbonates easily, just like CH also. Reacts strongly with CO2. Okay, so CSH are amorphous. That means they are not crystallized, they are not well organized. They look like forms like that. They have a structure that depends on the CPS.
Can you explain that again? Like if C over S is bigger than 1.5, then
if you have a ratio calcium silicium over 1.5, that means you have too much calcium oxide. And once you will consume all your silicate, there will still calcium oxide will still be here. And this calcium oxide will react not with silicium because silicium is not there anymore, silicium is eliminated. It will react with water and form also CH. But if your calcium oxide silicium oxide ratio is lower than 1.5, you will consume all your calcium oxide with the silicate from CSH. You won't get any residual calcium oxide to react only with water.
Is it bad to have it over 1.5? It's a silly question, I don't know.
Then it's the 1.7.
It's not silly, it's just that we don't have the choice with cement because cement contains a lot of calcium oxide. Because remember, it's C3S, so you have 3 times calcium oxide to silicium. And then you have C2S, so you have 2 times calcium oxide to silicium. So in the cement, you will have automatically a ratio over 1.5.
So the second one that you drew there, it means that it will consume all.
No.
Sorry. That's why I was so confused.
It's just the notation.
So it'll consume all of the calcium oxide and
With the
won't put,
silicium.
yeah, and won't, and it will,
Won't produce Portland diamonds.
and it will consume also silicone, or?
Yes.
Okay.
Calcium oxide will react with all the CA2 from CSH. But in the cement environment, we have way more calcium oxide than silicium oxide. That's why your CSH ratio in the CSH is over 1.5, and that's why we form also CH. Other important points, it may include aluminates, and in this case we call that CaSH. And you know the universe of these strange minerals, illumination, CSH, CaSH, it's bigger than the CSH because we have also with other materials you can have what we call KaSH, which is from calcium oxide. And you can also have what we call NaSH, that is from sodium oxide. But that's just that's an important point. So yes, they can be aluminates, especially in cements that contain secondary cementitious material. CaSH will form over CSH because if there is supplements in aluminates that don't come from C3A, aluminates that come from the secondary cementitious material, you will form what we call CaSH, and CaSH is simply calcium aluminate silicate hydrate. So, okay, you have a different observation. You have the CSH and the portlandite that is well crystalline inside the CSH, and then they say this is CaSH, but I'm not sure actually. I've never observed CaSH by STEM. I don't know if it's like this. But here you see the CSH crystal, amorphous crystal growth around the cement grain. Okay, now let's talk about portlandite. Okay, here it's very beautiful image. You can see the amorphous CSH and the crystalline portlandite. You see clearly the difference between amorphous compounds and a very crystalline compounds. Portlandite is the opposite of CSH. CSH is not crystallized at all, it is very amorphous. And portlandite, it's the opposite, it is very, very well crystallized. So, portlandite is stable, as I said before, at a pH above 12. That means it will dissolve at a pH lower than 12. There is competition between precipitation of CSH and CH. But if the silicate ions concentration in solution is high, CSH will precipitate preferentially. So first you form CSH, as we said before, by the reaction of calcium oxide, silicium oxide, and water. And then once all the silicate is consumed, you will form photondite from the reaction of the C and the water, the remaining calcium oxide with water. So I write that like silicate ions, but just write silicones, silicate ions. Anyway, you don't have to remember this H2HCO4 2 minus aqueous. You don't have to remember that.
So you said the first silicate will be formed with CSH and then CH will be formed. What does it mean when CSH will precipitate preferentially? You just read this.
This is a way of speaking we use in chemistry. There is always a competition. It's thermodynamic competition between the precipitations, and it depends on the concentrations, on the different concentration of ions in solution. And the precipitation depends on what we call the constant of precipitation, and the elements with the lowest constant of precipitation will precipitate first. That means CSH will precipitate preferentially. That means the constant of precipitation of CSH is lower than the constant of precipitation of photondite. Okay, so we've done with the hydration of C3S and C2S that react to water to form photondite, CH and CSH. And then we are going to the hydration of C3A. Okay, and this is where gypsum as a setting regulator will be useful, because in the absence of gypsum, I will write the formula for gypsum. Gypsum is calcium sulfate with 2 molecules of water. You can also have what we call it amyhydrate. Amy means half in Greek, so it's calcium sulfate with 1 molecule of water, and you can have amylase. It's just calcium sulfate. This is what you have to remember is cement as a setting regulator uses sulfate, and the source of sulfate is calcium sulfate. And there is a different type of calcium sulfate. You have gypsum, which is dehydrated, amyhydrate, which is only one hydration, and anhydrate, which is anhydrous, just plain calcium sulfate. And don't worry, even researchers that publish paper made the mistake of writing gypsum as plain calcium sulfate. But calcium sulfate, gypsum is calcium sulfate with water. Most of the time, gypsum is used as a setting regulator, but sometimes cementitious cement producer will use amyhydrate or iron. and sometimes they will use gypsum and anhydrite as a setting regulator. So these are the different types of setting regulator. There are sources of sulfates in the form of calcium sulfate, more or less hydrated. Okay. So in the absence of gypsum, in the absence of sulfate, you have a fast setting like a few minutes of the cement. And a fast setting means that it cannot be used properly, because if you want to construct something, you will have to have the time to use your cement properly. So you don't have to remember the equation of the compound that is formed in the absence of gypsum. Just remember that in the absence of gypsum, of the setting regulator, you have a setting of cement that is too fast. The reaction of C3A with water is too fast. So we use the presence of gypsum to react and to form what we call étranglite. You don't have to remember the chemical formula of étranglite. I wrote all my PhD thesis on étranglite, and I don't remember myself the chemical formula of étranglite, so I won't ask you the chemical formula of étranglite. Just remember the name, étranglite. Étranglite. So étranglite, it is hydrated calcium trisulfoaluminate. It forms by the reaction of C3A with gypsum. But then, when gypsum is totally dissolved, when gypsum is totally consumed to form étranglite, the sulfate concentration in solution is not high enough to maintain étranglite. So étranglite is dissolved and it precipitates again as monosulfoaluminate with an excess of C3A. So, so we have the dissolution of C3A that react with gypsum. That will form étranglite. Once all gypsum is consumed, there is no more gypsum, étranglite dissolved. And it precipitates as monosulfoaluminate. And étranglite is trisulfo. So étranglite is 3 sulfoaluminate. So, and here you have monosulfoaluminate, just one. So that means that étranglite needs more sulfates to be stable than monosulfoaluminate. And then we have a little asterisk here. Same process for C4AF with a slower kinetic. So that means we don't care about C4AF. Actually, C4AF will react with water and it will form this is a sulfoaluminate phase that contains iron, because in C4AF you have iron. So the hydration of C4AF give hydrogen, but you don't have to remember that. We will not go into the hydration of C4AF. The hydration of C3A is more important. So remember that in the absence of a static regulator, the hydration of C3A with water is too fast, way too fast, and the cement, the material is not usable. And so there is the reaction of C3A with gypsum to form gypsum and water to form ethernite. And then when all the gypsum is consumed, we form ethernite to form monosulfur aluminum precipitates again. So these are the equations. We have the dissolution of C3A. Dissolution of C3A, that means reaction of C3A with water. So you have the ions in solution. You have the dissolution of gypsum. I put an X because it can be gypsum or anhydrite. We've seen that before. And you release sulfate in solution. And then all these ions will combine to form ethernite. This is ethernite. And ethernite is very, not very strong mineral because its stability depends only on pH and temperature. Ethernite starts to be destroyed by high temperature, and high temperature means like over 40 degrees. So if you are over 40 degrees, we will start to destroy ethernite. Ethernite is also, as you can see, very dependent on pH, and it is stable at a pH between 10 and 12. So once again, rather basic pH. So water will destroy ethernite. So I have a diagram of stability of the calcium aluminum sulfate phase. You can see when the sulfate concentration here is very high, you are in the territory of gypsum. So if you have a very high sulfate concentration, you would precipitate gypsum. But it's not the case in the cement. In cement, you will have mostly aluminate and calcium. And then here you have ethernite territory. And once you reach a lower sulfite concentration, you get into monosulfur aluminate territory. It is quite short. Okay. So the stability of the hydrate, especially ethernite, it would depend on the temperature, on the pH, and also on the concentration of sulfates. Okay, now we're going to the column. No.
I think we really know what leads like within it. It's gonna be the minute if it was like dead. If it was pretty much dead. No, like 2 minutes and then you can start your shot.
Because I cannot cable my computer here and here. It's a bit-
Those outlets
I
work.
hope it's easy.
They work. I've used them before. If your computer is just dead.
Okay, so now you see all my. No, okay. Okay. So before going into pozzolanic reaction, do you have any question about this one of about the hydration of C3A, C3S, C2S? Any questions about the precipitation of Wittgenstein and anything?
What exactly is hydrogarnet?
It's a difficult question.
Why is it an F?
F, it's iron.
Oh, it forms hydrogarnet.
Yeah.
But I
Yeah.
thought F was hydrogarnet.
No. I mean, I circled F because to remember that hydrogarnet it's kind of a monosulfide, so sulfate aluminate compound, but with irons because it's from C4A.
So C4AF plus water forms hydrogarnet, which is
What?
hydro-
This is what?
What is it? I know that's what it forms, but what exactly is it?
I don't know. It's a mineral.
That's it. Okay.
Okay, I checked.
No, mineral is fine. That's all I knew. I wasn't sure if it was a liquid or rock or gas.
Okay, when I give you the slide, I will give you more information about hydrogarnet because it's a shame that I don't know.
Do we need to know it for the exam?
No.
Okay, then it's okay.
I just need to know if it
That's
was a
all.
rock or something.
Yeah.
Yes, it's a
Okay, cool.
You put on the board like the gypsum, the hemihydrate, and the anhydrate. And you said something that they're all like types of gypsum, just with different names, or?
Not really type of gypsum, they are all type of calcium sulfate. Gypsum is calcium sulfate, but with 2 molecules of water. Hemihydrate, one of 0.5. And you have anhydrate without molecular of water.
And so only the gypsum reacts with the C3A.
No, they all can, but they are put inside the cement. So it depends on the choice of the cement producer. Most of the cement producers they use gypsum, but sometimes they use anhydrite or hemihydrate, or they can use a mix of all those sulfate, calcium sulfate elements.
So are there not other forms of gypsum? Gypsum is only when there's calcium sulfate
Yes.
and water, that ratio of water together? Okay.
But it's important to remember that gypsum is calcium sulfate. You remember there is water, but most of the water around it is calcium sulfate. That's the most important thing because it's not gypsum as a magical compound. It's
Yeah.
a sulfate sources.
Okay, then wouldn't the hemihydrate and the anhydrate also count as gypsum because they're
No, gypsum is the name of this type of calcium sulfate. And anhydrate, there are other names
okay.
for other type of calcium sulfate.
And can you go back on the slide? You said that this, it dissolves and precipitates, and then, something.
This
Yeah,
one?
this one.
Okay. So this one is mostly the dissolution. The two first equation are the dissolution equation. Dissolution of C3A, the first one, and the second one is the dissolution of calcium sulfate. And the dissolution of this calcium sulfate and C3A release different ions into water, so calcium, aluminate, hydroxide, and sulfate. They are all in water, these ions, and they react all together to form Wittgenstein. so dissolution and precipitation. You have solid phases that dissolve into the form of ions, and then they precipitate again into the form of hydrates. And we call the hydrated phases, we call them literally hydrates. HI, CSH, porphyrdite, they are all called hydrates because they contain water. So now we will get into what we call the post-organic reaction. The post-organic reaction, it comes after the hydration of clinker. We're not into the clinker anymore, but the clinker will be involved. But the post-organic reaction don't come directly from the clinker. It doesn't come from the C3S, C2S, C3A, and C4A. Not directly, it will react with that. Post-organic reaction happens when you have secondary cementitious material. SCMs. Remember, I gave you the table from the norm, and there were all those cements with silica fume and slag, all that. These are the secondary cementitious materials. They were put into the cement to reduce the cost of the cement because the silica fume, the slags, the pozzolans, and all that, they were byproducts of other industry. So there was reducing the cost of producing clinker. And with time, we've seen that this cement with secondary cementitious materials, there are some advantages. For example, better durability, and also by reducing the clinker part, the more you use secondary cementitious materials, the less you use clinker. And that means if you use less clinker, you will produce less CO2. And this is now very important for the cement industry to produce less and less CO2. So that's why we have more and more secondary cementitious materials. So you have the secondary cementitious material from the table I gave you the last class, and more secondary cementitious material are tested and added to the classification. Okay, so the secondary cementitious materials, SCMs, they are formed of the phase triangle: calcium oxide, aluminum oxide, silicate. So cement is over there, very rich in calcium oxide. Most of the secondary cementitious material, they contain way less calcium oxide than cement. Cement is zero. They are over there, depending on the composition. But they contain mostly silicate and aluminum. So silicate and aluminum, they are good, but they don't react by themselves. We have to use to trigger the reaction. And what is mostly used is calcium oxide. That's why we cannot do pure cement made with secondary cementitious materials, even though some cement producers are doing cement without clinker. It's quite innovative and it doesn't work that much. We still have to use calcium oxide to trigger the reaction of silicate and aluminate, the pozzolanic reaction. Because what is the pozzolanic reaction? Is the silicate and aluminate from the secondary cementitious material, not from the clinker. The silicate and aluminate from secondary cementitious material will react with portlandite formed during the hydration of clinker. Okay? And then we form, once again, CSH by the reaction of silicate with water. And if you had aluminate, you will also form CaSH. So CSH of water. So, yes. Photolinic reaction takes place after clinker hydration because in order to have a photolinic reaction, we need the formation of portlandite. We need first to form portlandite, and then portlandite will react with silicate and aluminate from the secondary cementitious material. And so cement containing photolinic bonds have less mechanical strength at young age. Why? Why? Because the clinker part in secondary cementitious material compared to a cement that is 100% clinker, cement that contains secondary cementitious material will contain only 40% clinker. So this cement will form 100% of CSH after hydration. And this cement will form, you will have the reaction of only 40% of clinker. So as you remember, here so we will form 100% of clinker will give you 65% of CSH, the mechanical strength component. But if your cement is only 40% clinker, you will get 65% of 40%. I don't need to calculate, but you see that the CSH in the cement from 40% clinker will have less CSH. And then the rest of CSH will form after the reaction of the clinker, by the reaction of portlandite to form the rest of the CSH. So you will have a two-step reaction instead of a direct reaction and direct formation of CSH. And this is the default of this type of cement. They are less mechanical strength at young age. So nowadays it is something we can manage. So we use this type of cement in different type of environments. In standard there is recommendation of where to use different type of cement. And here is the heat release of the hydration. This is a typical curve we will see later of the heat release of the cement hydration. In black, you have a plain Portland cement, 100% clinker. And then you have cell 2, cell 3, and cell 3C. So cell 3A is like 60% clinker, and cell 3C is like less than 20% clinker. So the part of clinker here is around less than 20%, while here is like 100% clinker. So here you have the direct hydration, direct reaction. You see the peak, the reaction of C3S and the reaction of C3A, they are open at the same time. And here you have the second peak, it happens later. Okay? So just remember that the Pozzolanic reaction is a second step reaction of the secondary cementitious materials compounds with the hydrated phases from clinker. So it makes cements that are less mechanical strength at your gauge because we have to wait this two-step reaction process. While in some percent, 100% clinker cement, you have directly the reaction of 100% of your clinker to form directly all your hydrates. Okay, so this is how we can assess the pozzolaricity, because it's a property of your cement, by testing. So you put a bit of dry cement, powder cement, inside water, and you wait 1 or 2 weeks, and then you remove the cement with your filtration. You get the water that contains the cement for 1 or 2 weeks, and you make a filtration of calcium ions and hydroxide ions, and the ions concentration into your solution should be less than this curve here. Here, this is the curve of Portlandite precipitation. If you are above this curve, that means you have a concentration in calcium and hydroxide that is too high, and that means that Portlandite will precipitate. So your cement is not pozzolanic because it allows precipitation of Portlandite, and it hasn't consumed all the Portlandite. Okay, so now we go into the general principle of hydration, because now we just see the reaction, but what does it mean as a material? What happens to your materials? So cement is a hydraulic binder. We react with water to create a strong connection between the cement grain, and the connection will be created by the hydrates in between the cement. First, in your cement, your anhydrous cement, you have your grains of anhydrous cement. They are dry, they are just grains of cement. And then you get in contact with water. You mix. You have the formation of hydrates, which crystals around the cement grains. This is the initial dissolution. You dissolve your cement grains, and the hydrates in contact with water will precipitate at the surface of the grain. And during the dormant period, the induction period, the hydration continues slowly. The action of the concrete must be done during this period. You have still the dissolution of the grain of anhydrous cement, but you can see that there is more and more hydrates that protect the cement from water. That's why the hydration is slower. Then you have initial setting. The hydration accelerates and creates bridges of hydrates between the grains. So now your cement is binding its setting. This is the beginning of acceleration period, the connection of the grain of cement by the hydrates. And during the final setting, all cement grains are connected and linked by the hydrates that have precipitated at the surface of the cement grain. So the continuation of hydration leads to hardening and of acceleration period. Now the other grain are connected, and the connection only grows stronger. Okay. So we have initial setting. This is the curve of elastic modulus, and hardening that what will give more solidity and more resistance to your cement. So I'll show you the heat release curve, the simulation of heat release. First of all, you have stage one. You will know the first peak. It happens in the very first minute of the contact with water. You have the initial dissolution and the heterogenic formation. So you see how little time you have to get your heterogenic formation, and still we get heterogenic from the use of a setting regulator. So imagine without a setting regulator, you won't have any time to batch the cement. So that's why we use a setting regulator. Then we enter the dormant period, stage 2, induction period, increase in calcium inside the solution. The calcium ions concentration will increase, and then once you reach a certain point of calcium inside the solution, calcium ions, you have rapid formation of CSH and CH. They can precipitate. There is enough calcium for the precipitation of CSH and CH. This happens during stage 3. Then you have stage 4, the deceleration period. So slower reaction division through hydrogen layer. Yes, because now your grain of anhydrous cement, that is your producers of ions, they are covered with hydrates. So it's harder for water to reach these anhydrous and to dissolve these anhydrous ions because they are completely covered with hydrates. But the diffusion through hydrous layers still occurs, and you still have the hydrations that continue for time. And then you have steady state with slower reaction. So we say that a chemical reaction is over when you have consumed. You have reaction between A and B to form C. The reaction is over once you have consumed one of the reactants. But in the case of cement, the reaction is never over because you will always have the grain of cement. You will always have the cement, anhydrous cement that is present in your hydrate cement test. It will only be hidden behind the hydrate layer, thick layer of hydrates that connect the cement to anhydrous grain. And water is still present in your material because the cement paste is the porous element that contains water going through the porosity, what we call the porous solution. So the hydration reaction is never over. But we consider that the reaction is theoretically over after 28 days of hydration. Once your cement paste is hydrated during at least 28 days, it means you have your final hydrated paste. Even though, as I said, you still have hydrate, you still have water, and the hydration continues really slowly. At 28 days, you have your final materials. Final materials until it is in contact with the environment, and here other reaction happens. There are reactions with the environment, with chlorides, with carbonates, and etc. But regarding the hydration reaction, we consider it to be over after 28 days. Okay, so now we have the kinetics of the hydrate formations. In the first minute, you will precipitate, yes, it turns out we precipitate after a few hours. And you have CSH, and hydrogarnet. And monosulfate will precipitate once you see the etrangite will decline, and then you have the precipitation of monosulfate and also hydrogarnet that will precipitate with the monosulfate. So I'm not sure if it's hydrogarnet. Just remember it is the form from the hydration of C4AF. So this is the composition, and at the same time you see a decrease of the porosity of your cement that is filled with the precipitation of hydrates. So this is the composition. of your cement paste, you have residual anhydrous cement, mostly hydrates. You have the porous solution with a pH of 13. Remember that it's important. And you have airfoils inside your material. Because even though we try to vibrate, to tap the material, there is still air that is present inside the material. So this is the different parts of the cement paste: air, porous solution, hydrates, and residual anhydrous cement behind the hydrate layers. So this is how it looks. You have the original cohesion setting. Right after mixing, you have very little contact area, so a low reduce between the grain of cement. Slight contact between the cements. And after, during setting and hardening, you have the creation of the hydrates around the cement grain. So that means high react, so high reduce. Small particles of hydrates are formed at the intersection between grains of cement to connect all this grain of cement and giving cohesion to the cement paste. Okay. Do you have questions on this part?
Can you go to the previous slide?
Yeah.
Yes?
The previous slide.
Okay, this one.
Oh, I had one from the previous slide.
Can you explain that chart?
The what?
It's like minute, hour, and day. Can you explain this?
Okay, so this is the precipitation of the different hydrides through times. So in the few minutes, you have, it's difficult actually to, it's not precipitation, no, I don't know how to. So you have the different reaction with the dissolution of anhydrous bases and the ions that goes into a solution. So you have the precipitation of the different hydrates. This is the amount of hydrates depending on the time. And you can see, for example, here that you form. Yes, I know the CSH it shouldn't be here. Okay. So we have for example, it's better with the nitrogen. You see the formation of intrinsic, and then you have the decline of intrinsic. And when intrinsic decline, you have the formation of monosulfide. Okay?
Mm-hmm.
But this is not the best representation of what's happening. But actually, I had this representation, but it was all in French. So I searched for schematic representation in English, but yes, it's not the best. Maybe I should use the old one that I had in French and just try to translate everything. I will do that on the. Yes, it's better to do that because even myself, I'm not sure about the position of love and vice and all that. Yes, sorry.
Can you go back a few slides to the stages? Okay.
Okay, this one?
No.
No, this one?
The one more, I think. Yeah, initial set. Okay. And can you explain again why there's, in stage 5, there's slower reactions? You said something about anhydrous ions, or is it, I don't remember what you said. I didn't catch all of it.
Deceleration.
Yeah.
in final stage, why?
Why the reactions are slower in this stage? In
Yes,
stage 5,
because- Because it is more difficult for the water to reach the images grain of cement because they are
The cement
covered with
is-
layers of
Okay,
images.
I want to make sure. Okay. That's all.
Explain the third step and then the slide before it. You kind of spectate that part, the dormant period. You were explaining it and then couldn't write it down. Could you just explain that step again?
So first you have the dissolution and the transformation, and then you have the hydration that continues slowly, and you have the formation of the layers of hydrates around the grains of cement and they start connecting. But at this point, you have your hydration, but the grains they are not connected. So this is the time when we can do the batching of the compressed concrete, because after that you will get to stage 4. So that's why we call that the dormant period. The reaction, the hydration is happening, but your cement is still full. You can use it, you can batch it, and do whatever you want to do with it. But after that, you have the setting, and at this time, the grain are connected, and you cannot use your cement. It's started to leave. And after that, you have complete connection. That's the final setting. But after the complete connection, the complete hardening of your cement paste, you still have, it's not complete hardening, the complete setting. You still have what we call the hardening. That means the connection is still increasing between the grain. But at this point, your cement is set. Okay. So as I said, we have different parts inside our cement dishes. I will put cement dishes with cement paste. We still have the additional way. They are behind the hydrates. We talk about the hydrates, CSH, Portlandite, etc., etc. And then we have the pore solution and the porosity. So this is an important part of the cement paste. Cement paste is a porous environment, and you have different types of porosity, different pore size. Here you have the representation of hydrate. This is an example of hydrate porosity. So what type of porosity? The capillary porosity is the spaces between cement grains that are not filled with hydrates. They are usually about a micrometer size, because the connections is not complete. There are still what we call capillary porosity. But we also have hydrate porosity. That's porosity inside the hydrates. The hydrates, they are not plain minerals. They are specific geometry. As you can see here, this is electrolyte, and you see the porosity, for example, between the connection of the structure. And this porosity is nanometric. And you also have air voids, so that means bigger air bubble inside your materials. So porosity depends on different parameters. I haven't talked about that, but it is one of the most important parameters when we talk about cement and binder. It is water-cement ratio because I said cement reacts with water, cement reacts with water, etc. But actually, the water-cement ratio is very important to define the properties of a cement. It will define the porosity, so it will define the durability and the mechanical properties. If you have a water-cement ratio of 0.6, that's very high. That means you have very porous materials. And if your material is porous, you will have continuous diffusion of ion spaces, of chlorides, sulfates from the environment inside your cementitious materials. But if you have porous materials, you will also have less mechanical strength. So the specific amount of different elements of that compose the cement beds, it depends on the water-cement ratio. The porosity also depends on the type of CSH, because the way your CSH is arranged, the geometry of your CSH will strongly affect the porosity, since the CSH is like 65% of your cement base. And it will also depend on mineral additions, SCM, secondary cementitious materials. Because secondary cementitious materials are usually way thinner than cement. So even when they are unreacted, they give materials with very fine porosity, and the CSH and CaSH that will precipitate through the polymetallic reaction of SCM with the clinker hydrate we have a very thin porosity. So porosity depends on water-cement ratio, the most important, the type of CSH, and the mineral addition. If you have mineral addition, if you are SCMs, you will have a cementitious material with very thin porosity. Okay. So porosity is one of the most important parameters. It controls not only the diffusion of ion species within the cementitious material, but also the mechanical strength of your materials. And diffusion depends on pore size and interconnection of pores. I think you know that. Then we have another important element, the pore solution. So the pore solution, it contains alkaline ions and calcium ions. Because the cementitious materials is very rich in calcium bases. So the pore solution will also contain calcium ions. All the calcium ions from the clinker phases, anhydrous clinker phases, all of them won't react completely. So you have calcium ions, but also alkaline ions. So that means potassium ions, sodium ions. So that's why the pH of the solution is basic, because of the presence of the alkaline phases. We give basic pH around 30. And unique concentration in the pore depends on the age of the materials and the nature of the cement. The composition is affected, of course, by the environment of the materials. If you are in contact with seawater, for example, you will have chloride and sulfates that will get into your cementitious materials and that will get into your porous solution. And the porous solution is the direct contact of your cement with the environment, especially with water. And once again, the hydration reaction, dissolution and precipitation then take place in water, and chemical deterioration reaction that also takes place mostly in water by dissolution and precipitation. So the porous solution is very important for your to define your cement materials. So it has a big influence on the chemical equilibria and the migration of chemical sources. So these are some parameters, some characteristics of a porous solution. It's not very important to remember that. Just remember that the porous solution is very basic pH around 30. So what are the physical consequences of cement hydration? First of all, we have chemical shrinkage. Have you heard about chemical shrinkage? No? So chemical shrinkage, it refers to the decrease, to the reduction in absolute volume of solid and liquids in the cement base during the hydration. So yes, resulting from cement hydration. And the absolute volume of hydrated cement is less than the absolute volume of cement and water before hydration. So this is how it is reflected. You have a volume of solid that increase because you have Vattendyke and CSH. You have more volume of solid, but the total volume decrease. You have a decrease around 7%. This is the chemical shrinkage.
It takes a second to write all this. Just one moment, please. Did you say that it was the reduction of absolute
Yes, absolute volume.
of cementitious material?
Of the volume, the absolute volume of your products is less than the absolute volume of water and the cement grain. So you have a decrease in absolute volume.
And is 7% like the average value, or how much does it range between like 5 to 7%, 3 to 10%?
Oh yes, it's sometimes it's a range. We have a test to assess the real chemical shrinkage of your cement. So it's not an absolute value. So chemical shrinkage is the shrinkage connected to a chemical reaction. And then this shrinkage at molecular level, chemical level, it happens at a macroscopic level. And that's what we call step-desiccation, autogenous shrinkage. And it's the macroscopic volume reduction of cement base caused by cement hydration. You have a visible volume reduction caused by the hydration of cement. But the autogenous shrinkage, so the shrinkage of your paste, it is limited because, once again, the cement paste will set at the setting point. You won't have any more shrinkage because you have a few material. But the chemical shrinkage will continue at a molecular level. Macroscopic reduction of autogenous shrinkage is much less than the absolute volume reduction of chemical shrinkage because of the rigidity of the other cement paste. So we will continue to lose water. The material will lose water, but it won't affect, from a certain point, it won't affect your microscopic materials. You won't see the result of the shrinkage on your material because your material is set.
You're talking about autogenous shrinkage right now?
Yes, autogenous shrinkage regarding chemical shrink. Okay, so this is a summary of the hydration of cement. You have anhydrous cement, water. This is the initial state. And then, after hydration, you have cement paste, hydrated cement paste, with the grain of anhydrous cement, the water. You have the hydrates around the grain of anhydrous cement. You have porosity with water and air. Porosity in between the hydrated grain of cement connected together, but not completely and fully connected. And also you have porosity inside the hydrate. It's just that the porosity inside the hydrate is way more thinner than the porosity between your grain. So the hydration, as I said, the hydration of cement happens when all the water is consumed or all cement is hydrated, and both of these conditions will never be completed. So the hydration of cement is infinite. Okay. I want to talk about that. Yes, because it's important. Oh, la. So it's in French. I'm sorry. The optimum of hydration, the full hydration of cement, according to the Porous model, is reached for a water-cement ratio of 0.32. So the basis distribution after complete hydration at infinite time for a water cement ratio of 0.32 without external water supply. This is how it is represented. I'm sorry. So this was supposed to be here, of course, at 0.32. And you have the distribution of capillary opacity, capillary hydrate, anhydrous cement, and this is supposed to be the perfect water cement ratio to have the best hydration of cement at infinite time, because the hydration is never completed. It is happening to porous water.
Can you share this slide?
Yes. So, I don't know, I wanted to present some specific techniques to follow the hydration of cement, but maybe you've seen that with Benoit Hulin, right? Have you seen the thermogravimetric analysis with Benoit Hulin? No? Okay. So, I'll talk about Let's have some techniques to follow the hydration of cement, to understand the hydration of cement. The graphophyrometric analysis is a measurement of mass changes in the sample subjected to a temperature increase. We can apply that to cement, we can apply that to any element. For example, I don't know, you can apply that to chocolate. If you want to know what happens to chocolate when you put it into a cake inside an oven and you bake it. So you can apply this technique to chocolate because this is something we do in chemical school. But for cement, it is very convenient to follow the destruction with the increasing temperature of the different hydrate phases. You have your cement paste and you increase the temperature. You go from 0 to 20 degrees. First of all, you remove all the loosened water because, as I said, your cement paste is filled with water. And then you remove, as you get higher in temperature, you will remove the connected water. And then you will remove the CO2. And depending on the mass change, you can quantify, depending on the mass change and at what temperatures the mass change happens, you can quantify the hydrated phases. For example, here you have a mass change related to Portland, around 500 degrees. So you have the samples, it was 5 grams at 450 degrees Celsius, and then it is 5 grams at 550 degrees Celsius. So you lost 1 gram between this temperature and this temperature. And you know this temperature is the destruction of Portland light. So you know that the mass loss is caused by Portland light destruction. So you know that at this point your sample contained 1 gram of Portland light. So it is very convenient to quantify the Portland light or the calcium carbonate contained of your samples. We also have, I've talked about that the last time, X-ray diffraction. It allows the detection of crystalline phases, so it has to be visualized, by comparing the obtained refractograms with a database. And it is a technique that is quantitative, so you can observe certain phases, and by comparing to the database, determine that this is this exact phases, and you can also quantify the phases. But it is very difficult to quantify the phases. But the limitation with cement is that it's only for the detection of crystalline phases, and the CSH that forms mostly of the cement base is amorphous, it's not crystallized. We also have magnetic intrusion transmitter. This is a technique that allows the visualization of the pore size distributions, because as I said, the pore size depends on the amount of hydrates, the connection of the grains, and you can see the different size of porosity. For example, here, this is the capillary porosity. So we have a big peak corresponding to an important capillary porosity. So a porosity caused by the connection of the grain of cement. And here you have the porosity of hydrates. So these elements contain more hydrates than this one that contains more porosity between the grains. So that means there are less hydrates here and less connection between the grain, so more porosity between the grain, more porosity, capillary porosity, and here more hydrates, so more hydration. So that's why this technique is convenient to follow the hydration. But it is very dangerous because we have to use mercury to do that. Then we can observe our element by SEM, and so microscopy, electronic availlage, SEM, and electronic microscopy. This is microscopic observation. You can see the hydrates, you can see the cracks, the degradation, and you can couple with EDS, EDS probes, to quantify the observed phases. So by EDS, you can watch the phases, and EDS will say, okay, here you have calcium, here you have silicium, and you see the where are the located your hydrates. You have also microtomography, which is a 3D reconstruction of the samples using successive images, and you can see the degradation and the porosity of your materials with that. Okay, so I'm done, and we completed the class. If you have any questions.
That's like, what is EDM?
EDS?
Yeah, it is. What is EDM?
I don't remember. I checked. I'm sorry. Okay, EDS is energy dispersive X-ray spectroscopy. EDS or sometimes EDX. Oh no, they have left. They haven't signed.
No, that's what
Anyway. Before leaving, you have to sign the. Oh, you haven't left because before leaving, you have to sign the. Okay.
Are all these measurements for the hydrated cementitious material, or for are any of them for like the clinker, like
Of course, you can use it for the clinker. Of course. The microscopy is trying to.
I think all three of us combined will have one batch.
So, power and
Body.
but you can also
What the
observe that with the mercury intrusion, you have to get bulk samples. So
Wow.
with
That is
powder.
a lot of
This one
cement.
calls
Good job.
powder.
Well, I did something more basic.
Your unusual cement.
Mine was like,
It's perfect to be analyzed with that.
this is mine.
It's very convenient.
Dude,
And
look how neat this started off,
this one.
and look how this ended.
It's
Like,
not
it reached a point where my hand hurts.
convenient because the
I
clinker
my hand feels fine. I can't listen and write.
was immunotensine
I just want to be a bit more positive
very
as
low
far as
temperature, higher than
than drawing
1,500 degrees. And here you will just increase the temperature of something that has been already calculated, so
I
you
will
can.
need to file this, make this neat, and I'll send it to you.
No, you don't have to. It's fine.
You should really, even I can't understand. Even I can't understand what I've written.
Yes.
Is
But
broad
now you
enough?
have to
Even
change
I'm fine.
See, you got a
Yes, because
It was just a